Just for people who are joining, we're just gonna wait for a second before we start, just to make sure that everyone's in. All right, I think we're going to start now. Hey, everyone, I'm Chinmay. I'm on the dev team for the Datathon, and I'm going to be the moderator for the class today. Welcome to our introductory machine learning class. It's going to be taught by Josiah Code, as you can see here. He's the teacher, and he is actually the founder and the president of Datathon, and he has also interned at Facebook, Microsoft, and the CIA. And currently he's doing reinforcement learning research at Carnegie Mellon. So with this, Josiah, take it away.
Thanks, Chinmay, and thanks everyone for being here. If you feel comfortable to turn on your camera, that would be awesome. I just love to see people's faces. I think it's really hard not to be like in a classroom, and so it's just fun to have that interaction. So yeah, if that's something you're comfortable with, to go ahead and turn that on. So I wanted to start just by wondering, I think one of the advantages of having an online event is that we can join from everywhere and from all different walks of life. So I know there's people from just every walk of life here. So even though I'm not in Texas, the Datathon is centered in Texas at Texas A&M. So I want to just ask as an introductory question, who thinks they're furthest from Texas A&M in the world right now? So if you're, yeah, who thinks they're furthest? Pitch up. Is anyone outside of the US on the call? Just wondering if it's like 3 a.m. for anyone. Hopefully not. Hopefully it's a good time for people. Is anyone on the East Coast?
I'm in Charlotte.
Charlotte, okay. That's pretty far. Is that John? John said that?
Yeah.
But are you a student, John?
Yeah, I'm at A&M. I'm doing a Master of Science in Statistics.
Okay, right on, cool. Okay. Is anyone in, let's see, California right now? That's the other end of, or the West Coast? Okay, cool. So we are, I guess, more East Coast leaning, more or less. And I'm guessing a good amount of people are in Texas. Well, I am up in North Idaho right now, personally. And funny thing, actually, Chinmay is also up here. We're both good friends, and so he's actually in the other room. But that's just a little bit into my personal life. I do really want to get friendly with you guys because if we were in a class, I would really try to get to know all of you. And that's just really what I love in this job, is just to get to know the students. And so unfortunately, we don't have a lot of time, so I'm just going to get into the talk. But please post your questions during the talk. Chinmay will be watching that chat, and he'll pitch up if he thinks that I need to stop at any point. I'll also stop a couple times. I don't want anyone to get lost. So this is an interactive lesson, and I hope that everyone can follow along. Okay, well, I'm going to start by posting a collab link in the chat. And so how this is kind of structured, if you don't know, the Getting Started in Machine Learning is a 2-hour course. And the first hour is going to be a little bit more theoretical. And then we are going to do some coding, but we are going to talk about some of the equations and some of the intuition behind machine learning. And then we're going to go in the second hour into some very practical state-of-the-art machine learning methods that a lot of people do use, and that will really help you in your data science projects. It's going to be, so that's kind of the outline. And so we're going to get started. So the collab should be able to, you should be able to click on it. Note that if you try to edit it, it might look like you can, but then if you try to save it, it will say save a copy to your drive. So just go ahead and do that. Click save a copy to drive. That way you can have the notebook after the lesson and you can edit it. So the notebook, you should be able to edit it all you want, try out different things. And so, yeah, that should be good for us. All right, we're going to get started with, I'm going to share my screen. And we do have a lot to cover today, so I'm sorry if I go a little fast. Please just post something in the chat and we'll try to get back to it. Well, we're going to start by just doing a linear regression refresher. So maybe some of you already know linear regression. And so linear regression is probably the first algorithm you'll do in like maybe an introduction statistics course. But what I'm going to teach you today, I love taking something that we all know and then building off of that. And so what I want to show you is the bridge between linear regression and machine learning. So just to make sure we're all on the same page, in case someone needs a refresher for linear regression, I'm going to start with a short video on introduction to regression. Let's see. And Chinmay, can you see my screen?
This tutorial is an introduction to regression.
You can also hear okay?
Yep.
Okay, great.
There's an X variable and a Y variable in this case. The independent variable is on the X-axis and the dependent variable is on the Y-axis. And we try to form a relationship between these two variables and draw a line, in this case a straight line. And over the next series of videos, I'll explain what all this means. What we try to understand is as the independent variable is moving or changing, what happens to the dependent variable? Does it go up or does it go down? How does it change? If they move in the same direction, if the independent variable increases and the dependent variable increases as well, like this, we say there's a positive relationship. If on the other hand, as the independent variable increases and the dependent variable decreases like this, we say there's a negative relationship. The line would look like this, go downward. In linear regression, we try to make a line. A line to make a linear regression, the key is on line right there, a straight line. You can also do curved lines, but for this topic, it's all straight lines. To actually conduct regression, I take observations, and I'll just plot some more observations in here randomly. I'll stick them in here like that. And I try to find a line that will fit, a straight line that fits through all these different points. And this is called my regression line. And it's based upon the least squares method. And in the end, I want to minimize the difference between the estimated value and the actual value. I want to minimize my errors. This line will have a lot of errors if I compare the actual to the estimated value. And again, the point is to minimize these errors or make them as small as possible. Now let's imagine I put study time on the x-axis, or make that my independent variable, and the dependent variable becomes grades or GPA. As study time increases, grades should go up. There is a positive relationship. In regression, we develop these equations like this. In this case, y hat is estimated grades, and it's based upon, or it's equal to, b naught plus b1 times x, where x is study time. B naught we derive mathematically, and it is the y-intercept. B1 we also derive mathematically, and I'll do it in a later video, and it's the slope of the line. In this case, the slope is positive. In the next video, I'll discuss how you develop these equations. Now, if I change the x-axis to time on Facebook, we see a negative relationship. More time on Facebook, grades will suffer and go down, a negative relationship. What we're estimating is still grades, estimated grades, is equal to b naught minus b1 times x, where x is time on Facebook. B naught is still the y-intercept. The y-intercept. And it is a calculated value. The slope of the line is negative b1 because it's downward sloping, negative relationship. And as I said before, I'll show you how to calculate this equation in the next video. The x is the independent variable. the y is the dependent variable. The x is what we control, what we manipulate, what we change. And the dependent variable is the outcome. So study time is the independent variable. It's what we control or manipulate. And your grades are dependent upon how much you study. Now this looks really ugly, and it's what I'll talk about in the next video. But I'll step you step by step through it and hopefully make it simple for you.
Okay, and that's the introduction to linear regression. Okay, so maybe some of you already knew about that. Maybe that's the first time for people. But what I want to do next is draw a bridge. Can you see? Yeah, my screen. Okay, so draw a bridge between what we just learned and machine learning. And so I want to tell you that actually machine learning, we can formulate linear regression. Linear regression is a machine learning problem. And that we might not think about it like that at first. I definitely did it for years because linear regression was something I learned on pretty early on. And then machine learning was always this like far out topic that was super complex. And it seemed so far distant from like what I knew. But what I want to tell you is that linear regression is actually machine learning. I'm going to show you why. So just a little clarification, that video said B0 and B1, B0 for the y-intercept and B1 for the slope, but we're going to use B and W from now on. And I'll tell you, that will become apparent why later. It doesn't change anything. So like the video said, a linear regression, in the case that you only have one dependent variable, and in data science we often call the independent variable, like the x, we call that a feature, and the y, the dependent variable, we call that like a target. And so that's kind of just data science terminology. You might even hear it referred to many other ways. So here I have the target variable y hat. Sometimes this is called the response, predicted, dependent, or label variable, just depending on what field you're coming from. And then the x is sometimes called the explanatory variable, predictor, feature, signal, or independent. So there's a lot of different ways that it can be called. Now the difference, as the video said, between why you would put a caret on top of the y, when we actually get a data set, so say we query like 10 people out of a class for their grades on a test and how much they're on Facebook, that would be the x and y. Now, if we tried to find a value for W and B that would create a line through your X and Y data, then then plug in different study times, theoretical study times for the X, or theoretical Facebook times for the X, then we would get a Y hat that would lie along the line. And so that's our predicted value. And the goal of machine learning is we want Y hat to be as close to Y as possible. So we want to find a model that, given time on Facebook, we can predict Y hat the grades. Now, when you look at machine learning, you'll see some pretty crazy equations, but all models. Okay, so machine learning is better called model fitting, and what a model is it's just an equation or a function of your features. And so here we have Wx plus B. And so that's a linear model, and linear because it's a linear transformation of our feature X. When we say to fit a model, what that means is that we're going to be trying to find values for our parameters. So let me back up a little bit. So in a model, you only have two types of letters there, right? So there's 4 letters there, and the y and the x, those are your data. And so you'll have your data variables, and then you'll have your parameters. So the difference is that data is what you get from your training set. So maybe if we query 10 people in a class about their time on Facebook and their grades, then that would be our y and x. So in that way, we can't really change that. We're given that. But given the data, we can find values for our parameters. So parameters are things that we can adjust. And we're going to experiment a little bit with us adjusting the parameters by hand today, but we're also going to show how you can use a computer to adjust those parameters. And when we say model fitting, so that's what a model is. It's a combination of, it's an equation of data and parameters. And when we say fitting, it's just finding the values for W and B which make the model best like agree with our data. And so remember that, and so I'll show you a little bit more later. Now, a question arises is, well, okay, so if that's what model fitting is, how do we find the values for W and B in this case? And the answer is that the best parameters of W and B in this case achieve the lowest loss. So a very important topic in machine learning is a loss function. Now, anything can be a loss function, and if you look in the machine learning literature, there can be some pretty complicated loss functions. But there are a few qualifications, and this gets pretty theoretical, but there are a few qualifications for what quantifies a loss function. It must be easily differentiable, and that gets into some deeper math. It always must be a positive value. And so if our goal is to minimize loss, then the loss closest to 0 is going to be the best. So the computer's goal is to minimize this function. And so it's going to be able to adjust W and B to minimize loss. So loss function is a function of your parameters. And so here we have this fancy L, and that stands for loss function. And you can see that the loss function is a function of our parameters. And in the video, he mentioned ordinary least squares. Statisticians will call it OLS, or ordinary least squares, especially for linear regression. But this is actually in more machine learning literature also called mean squared error, which is the most common loss function. And so how MSE works is it's a loss function which takes your parameters, in this case W and B are our parameters, and it's going to sum up the difference between every Y data value we got and the predicted value that we predicted for that Y hat. So if we collect a bunch of samples of Facebook time and grades, then all the grades will be the Y, and then if we try to fit a model to that data and then we predict grades, that will be our Y hat. And so this is a pretty, MSE stands for mean squared error. And so error is the error here, the subtraction we do. And then squaring it, that's where the squaring comes from. And then mean is where we sum over. And this isn't, I guess, exactly mean squared error, because we would probably divide it by 1 over n. And there's also this funky 1/2 out in front. But actually, this is dividing it by 1 over n and putting the 1/2. Those are all what we call like monotonic transformations, which is a really fancy way of just saying it doesn't matter. If the computer minimizes true MSE, it's going to minimize this function. So you can look over that. So, but I did say that loss is a parameter of W and B, right? Well, it's because of this. Y hat is a function of W and B, right? From this model up here. And so we can plug in our model for Y hat. And so you can see then that the parameters we choose for W and B are very important, as they will affect the Y hat, which will in turn affect the error and overall the loss function. So by adjusting these W's and B's, we can minimize this loss function. And so that's what we're going to do. Now,
by the way,
yeah,
there was a question.
Okay.
And someone asked, does a loss function always mean mean squared error?
Okay, so good question. So nope. A loss function only has to do these two things, to my knowledge. Yeah. So anything, you can make up any loss function and just ask yourself, is it differentiable, and is it always a positive value for any of the input space? So yeah, we can make up any arbitrary loss functions, and like I said, in ML literature, you'll see some pretty crazy loss functions. The general idea behind loss functions is you always make a loss function that tries to quantify what you're trying to punish. That's pretty abstract and theoretical. So, but no, MSE, there's many other loss functions. Okay.
Sorry for interrupting again.
Yeah, no,
but
go
just
ahead.
to branch off from that, there's also another question that said, how do you determine which loss function is the best?
Yeah, how do you decide that? So you'll see there's certain time. Okay, so once we get to classificate, it depends on a lot of things, but mostly the domain that you're working in. And so if right now we're doing regression, which we're working with numerical values. So MSE works very well for numerical values, like if we're trying to predict grade, right? Which is a scale from 0 to 100. So that's a numerical value. But say in the next hour, we're going to be trying to predict classes through classification, like, you know, red, blue, green. And then how do you can't really use MSE if your outcome is that you're trying to predict is like red, blue, green. So you'd have to find out a different loss function to use on that. So it depends on the domain. Okay, so the next thing is there's a score function as well when we talk about machine learning. And so the loss function, the difference between score and loss, they might seem similar at the beginning, but they're slightly different. A score might also be called an evaluation metric. And the score is for humans. So a loss doesn't really mean that much to a human. Like if I report a loss of like 12,000, that won't mean much for a human. The computer uses a loss because the computer says, okay, for this setting of WMB, we have a loss of 10. And for this setting of WMB, we have a loss of 20. So we're obviously going to use the first setting of WMB. And so the computer can interpret loss that a human can't. So that's why we have a score function, which will be for the human. So in the case of linear regression, we use R squared as a score function. But the score function might not be differentiable and might not be a positive value. So the computer can't really like maximize a score function or something. Okay, so that's a slight difference. So what we're going to go into next is actually fitting a model by hand. And I want you to gain the intuition for what it means to fit a model. So here we have some dummy data. I'm sorry, it's kind of abstract. Maybe it'd be better if I came up with imaginary, a feature and target. So yeah, I can't really think of anything, but okay. So X is our feature and Y is our target. You can maybe imagine something. Maybe the feature is, I was going to say time on Facebook, but you can't really spend negative time on Facebook. And Y might be something like grade, but yeah, whatever. So anyways, this is just arbitrary data. And we can already tell it seems to have a linear relationship, right? So it would make sense to try to fit a line to this data. If you were in Seth's data science start here class, you might not know that you can actually run a cell by clicking this play, or I like to just hold down shift and hit enter. That's just a shortcut to run the cell. So you also have to run the cells in order. It will not work if you don't run them in order. So this is some data and we just got to run. I'm not really focusing on the code for this. The theory is the more important part. So don't worry that you can actually see the code if you double click like a block. But I wouldn't worry about it. So what this cell is doing is you're going to be able to play with the WMB, and you got to remember our model. So our model is being shown here, right? So the model in this case is a line because it's a linear model. And you can see here that we've filled in the values for WMB in this model. And right now I have a setting for W, which is 0, and a setting for B, which is -25. And you can see that in the model, right? Y hat, the value that we're going to predict for Y hat is W times X plus B. And so right now, I mean, it's pretty easy for us to see that the line does not fit the data at all. Like it's a very bad fit, right? Because it's all the way down here. What if we did go with this model? What we would be saying is that for any value of X, our target would be around like, yeah, -25. That's obviously doesn't fit the data well. Now, what you can see over here at the same time, what's happening is this is what a human sees. And so by a human, oh, and also we can see our R squared is -52, which is horrible. I mean, it's not even, yeah, it's very bad. R squared should go from 0 to 1. So anyways, so a human can see that, right? But what does the computer see? In the computer's mind, the computer has this idea of what's called a lost terrain. And you see this little dot on the lost terrain. You can see that the dot lies on in the position of W -5 and B, or wait, it's yeah. The visualization is kind of weird. Let's see if I can move it around. Okay, so, oh, let me move it over here. Okay, so the W lies on, is set to 6, right? And the B is set to 18. And so that's where that dot lies. And it's a little, I mean, if you move it around, you'll see that the dot goes up and down this loss terrain. And so what the computer is going to be trying to do is adjust the W and B parameters, and thus they're adjusting the dot on this plane. And they're going to be trying to bring the dot to the bottom of, well, it's not a plane, of the terrain, of the, there's a more technical term for it. I forgot, but I'm going to call it a terrain. So they're trying to bring, and it's kind of like a bowl, right? They're trying to bring the ball to the bottom of the bowl. So the computer is going to be trying to find the values for W and B, which bring the ball to the bottom of the bowl. Okay, so how is that bowl formed? How's that shape of a bowl formed? Well, the loss terrain is formed by, what the computer's done is it's formed this bowl by evaluating, remember the loss function, it's a MSE, a difference of every point to the line. And so back to the video, remember how he drew a line, an error line from each point to the projection of that point on the model, and that's your error. And so by summing up all those errors from your data to your model, you get one single number, which is your loss, your MSE, for this setting of W and B. And that loss, I can't see it that well, but it looks like somewhere around like 20,000. So if you sum up all of the differences between these dots and the line, you'll get a loss of somewhere around an MSE of around like 20,000, which is obviously very high. And so we want to mess around with this a little bit more and try to find, and you can see how the ball is moving to the bottom. Okay, so it looks like maybe W at, oh yeah, maybe 2, and B at maybe 0. Nope, W to 1. And watch how see how the ball's moving down. So now there's still, you can see that no model's perfect unless all the data was lying. If all the data was lying perfectly on the line, then there would be a loss of 0. But in this case, there's some scatter. So there is still some error, right? From each point to the line, there's some error. And so all of those errors summed up together equal 37. And but it kind of does seem like the ball kind of seems at the bottom of the terrain. So it looks like we've minimized the error. Okay, any questions on that? Because that is the essence of all machine learning, trying to get the ball, trying to find the parameters which minimize the loss. So I'm just going to open up to a minute of questions.
Yeah, if you all have any questions, feel free to text in the chat. You could also unmute yourself and ask any questions if you have one.
Okay, well, yeah, feel free to post it in the chat. I hope everyone's able to follow on. All the code should be perfectly runnable, but if it's not, please post it. It's not you. It's not you. It's just, I don't know, maybe, stuff happens. So, all right, here's another plot. It's not anything different than what we just saw, but it's kind of a little bit nicer to play with. Let's see. It's going to show up. If it doesn't show up, that's fine. It's exact. Okay, yeah. So it's just a little bit nicer visualization. It's exactly what we saw before. But you can move your cursor around, and that represents. So you are almost operating as the computer right now, trying to find the values of W and B, which minimize the loss. Okay. So obviously, that's time consuming and kind of ridiculous for a human to try to mess with all the parameters. So we would like a computer to be able to find the values of W and B, right? So how we can do that? Well, formally, we want the computer to solve this problem. We want it to find the parameter settings. And so theta represents any parameters. In our case, theta equals like W and B, right? So any parameters. We want to find the parameter settings which minimize the loss. And that's done just with calculus. It's actually like if you take in like a calculus 3 class, you will have all the math you need to solve this problem. Actually, in the case of linear regression, you only have to take like a high school calculus class to solve it, because in the case of linear regression, you see how it's a bowl? That bowl shape is actually called convex optimization, and it's really easy to solve, right? All you have to do is take the loss function, take the first derivative of it, and then, well, I guess the gradient in respect to W and B, and then set it equal to 0, and then just solve analytically, and you'll pop out the exact values for W and B. That's convex optimization. The problem is most loss terrains are very complex. And so instead of one bowl, it may look a lot more like rolling hills. And so we have this problem of we can't use that simple method. So we have to use a method called gradient descent, which really was what started the entire machine learning revolution. And we've made little adjustments to it, but it's still what we use today. And so gradient descent is what the idea is. Let me put the ball back over here. So the idea is anywhere that the ball is, we want to find the value of steepest descent. And let's see, yeah. So you see how the ball's there. And we can intuitively see that given where the ball is, which is our initial guess, we can find a gradient, a way to move that ball that would move it down the bowl, right? And so that's called, just the gradient at the ball is the slope of the terrain for each parameter. And then by moving some direction in that angle of steepest descent, we do what's called gradient descent. And it's a very simple algorithm, like it's a 2-line algorithm, which is compute the gradient and then move some small distance in that gradient. So like for here, I see that the gradient would probably would move W to the right, and B, you can kind of see which direction the gradient's bringing the ball, right? And so we want to move the ball a little bit in that direction. And it's like, well, why don't we just move the ball to the bottom of the bowl? Well, that's because we often don't have a bowl shape. So we kind of just have to move like little increments because we can't find the global minimum. So I don't want to get too complex, but so the idea is we just want to go down the slope like this, and we want to find that gradient, and then we want to move down that gradient. Okay. So the computer can do that pretty easily. So I'm going to introduce this library that maybe you know about. It's called Sklearn, and it's a really nice library if you're just getting started in machine learning, because it provides a amazing, clear, consistent API for machine learning algorithms. So you can use sklearn in Colab by just saying from sklearn.whatever, import whatever, and you can look up sklearn's documentation to see everything that they have. They have a lot. And really easy how you call a machine learning algorithm from sklearn. You just create an instance of the model. So in our case, linear regression is the model. And then you just .fit with X and Y. And remember what .fit means. It's just finding the values for W and B, right? So this is our X and Y. And we want, up here, we tried to find values by hand that were good for W and B. So let's see what the computer finds. In the end, so this model will, after we do .fit, a model, remember, is just pretty much it will save the values for W and B, which fit the line. And so you can get those values for W and B by getting the coefficient, which is our B, and our coefficient would be our W, and intercept will be our B. And I've just kind of printed that out here. And so you can see that the computer chose 0.89 as our W and 0 as our B. So the computer found the perfect settings for W and B. Note the R squared, it's a little bit hard to see on my screen, but I've also included the R squared value, which is, remember, the score, and a little bit different than the loss function. So you can see up here, once we get pretty close to, I think it was like something like this, right? You can see our R squared is 0.87. So pretty much the same R squared. But you can see how that's different than the loss, right? The loss is 37. So what does loss of 37 mean? I don't really know, but I know that R squared goes from 0 to 1. And so an R squared of 0.87 means that we're doing a pretty good job of fitting the data. So that's why score is more interpretable. Okay. Yeah, maybe you notice that this R squared is a little bit lower. Theoretically, it should be higher. I'm not really sure what's going on there. Maybe some rounding errors and stuff. So that's the bridge from linear regression to machine learning. And now I want to bridge machine learning and linear regression to neural networks, because this is something that only clicked for me after years of kind of studying machine learning, that actually a neural network could represent a linear regression quite easily. And because no one had taught me that, and it seemed so like the first thing that someone would teach me, when I actually found out about it, I was pretty skeptical, and I'm like, no way. But yeah, I mean, a linear regression can be thought of as a neural network. And so that's what I'm going to show you today. I'm sure maybe you've heard of neural networks, maybe not, but neural networks are the building blocks of the hot field known as deep learning. And deep learning is the king of models when it comes to unstructured data, like pictures, videos, natural language. Maybe you went to Ankit's talk that talked about using deep learning for image recognition and whatnot. So yeah, it's definitely used for that. But sometimes deep learning is actually used for like structured data in data science as well. So it's definitely a good thing to know about. Really, a neural network is a model, kind of an all-encompassing model, and that's why we like it so much. So the linear regression model that we learned is very restrictive, right? It's only good to model data that kind of falls in a line. But what if your data like doesn't do that and does something kind of crazy? Like there's not probably a linear relationship between pixel values and if it's a cat or dog, right? There's some really crazy function and like that model that defines that relationship. And so a neural network is sometimes called the universal approximator. So this is kind of an introduction to neural networks. And this by no means is a neural networks talk. That's a whole different thing. But I just wanted to show you how, and there's different libraries for neural networks and everything. So I just wanted to quickly show you how linear regression could be represented as a neural network. Well, if you're not from like a technical field or computer science, I'm just going to introduce like what's going on here. This is a graph, a directed graph, where we have nodes, which are the circles, and edges, which are the lines, and they're directed edges. And so what does this mean? Well, over here we have the linear regression line, which we learned earlier. Ooh. I'm not going to take time to fix that.
The setup, you need to run the setup.
I need to run setup. Okay, thanks. You got to run them in order. Okay, so, okay. Well, when we have a node like here on the left that's feeding into an edge, we call that an input node. And an edge on the, a node on the other end of the edge is called an output node. And so a node represents like information. And so X is like one of our pieces of information, right? And then when it gets, an edge comes out of it, that represents the information getting multiplied by a parameter. And so X gets multiplied by W, right? Well, and then there's an edge down here, and that's our parameter B, right? And what does B get multiplied by? Well, kind of nothing, so we just put a 1 here. And so the output node, the function that happens in an output node is it just sums all the information coming into it. And so what happens here is we take a node, we multiply it by an edge, and we take this node, we multiply it by an edge, and then we sum it together. And that's the value that gets represented in this node. And so this node that happens here, it's just a graphical representation of what we've already done. This node represents the model that is WX plus B. And so neural networks are much more complicated. They get more complicated, but really that's the basis of, and so the idea behind this is it kind of comes very loosely from neuroscience. The idea is that like neurons that fire together, that wire together, that's the idea. And these come from the idea of like neurons and synapses in the brain. And if like this node, the idea is that this node, if it needs to listen to the X, if the X is important, it will learn to strengthen this edge by increasing the edge weight here. And so you can see how when I increase W, it increases the edge weight. And that's, yeah. So you can play around with that a little bit, and try to convince yourself of that connection between the neural network and the model. I know, yeah, we're coming a little bit close on time, so I'm going to move on. Well, what about if we have we've been talking about X as a feature, a single feature, but a lot of times in data science problems, we have many features. And so we're going to try to expand our models and move to more complex models. And so there's different ways. There's two ways that we can expand, make more complex models. One way is by having more features, right? And so what I'm going to, that model that we had up above actually could still work for multiple features if we think of X as a vector instead, and W as a vector and B as a vector, which a lot of machine learning is very vector and matrix heavy. And really just a lot of matrix multiplication and whatnot under the hood. So it's really good to be very comfortable with linear algebra, like especially just the basics of arithmetic and linear algebra and vector multiplication and matrix multiplication and everything. But anyways, so here's a data set, a real data set this time. And we're gonna try to fit a model to try to predict miles per gallon for a car, given some of the other features. And so I'm not going to go into what this code is doing. If you attended Seth's talk, you might already know. If not, go back and watch his talk, and then you'll understand this code. But what we're doing here is we're importing a data set. So here's each row represents a car, right? And some features about that car. And maybe now's a good time to mention that a lot of times there's not something inherent about, like, why do we choose miles per gallon as the target and everything else as features? That's kind of up to the data scientist to choose. But sometimes there's intuition about what's a response variable. So miles per gallon kind of seems like a response to all the other parts of the car, right? And so why would we want to fit a model to this? Well, say we're a data scientist working for a car company, and they want to, there's a bunch of engineers sitting around in a room and talking about this new car that they want to build, and you're the data science consultant. And one of the concerns for the car is that it has good gas mileage, right? And so the engineers could, one way to do this is the engineers could go through some pretty crazy equations, calculate everything about the car, the aerodynamics, about this theoretical car that they want to build, right? The aerodynamics, all this stuff, and maybe come out with a miles per gallon. But you as a data scientist say, well, that will take too much time. Let me just go online, find 1,000 other cars that have the model year, acceleration, weight, horsepower, displacement, and cylinders. And I'll fit a model that will use all of those features to predict miles per gallon. And so for this new car that you want to propose to us, just give me those 5 features. 5, right? 6 features. Just tell me those 6 features, and I'll be able to tell you probably what the miles per gallon of the car will be, given other cars. And so that will save a lot of time for the engineers, and they'll be very happy, and you'll get promoted as a data scientist. If only life was that easy. But anyways, so what we are doing here is we're just visualizing the data. So I've chosen 2 features now to visualize for you, and weight and horsepower are X and Y, and miles per gallon is the Z. And so you can actually, this is a real nice visualization. You can go, each dot represents a car, right? And you can actually see all these cars and their horsepower and weight and stuff. And you can kind of see that there seems to still be a linear relationship to these. It seems like that if we fit an extension of a line, which is a plane is a line in 2 dimensions, and a hyperplane is a line in 3 or more dimensions. So anyways, it seems like we can kind of fit a plane to using horsepower and weight to predict miles per gallon. So that's what we're going to try to do. Oh,
just by the way, we've got 5 minutes left until we'll have to open up for question and answers. So okay. Just as a head up.
Thanks, Jimmy. Yeah, so here we, again, just import linear regression. Remember, not much is different. We just do .fit. Notice that nothing has changed about how we do this with more features. So again, we're just using, and see, we have two features now, weight and horsepower, and then a target of miles per gallon. And then .predict is on any machine learning model from Sklearn. That's what we're going to use to find the predictions. And so now, using those predictions, I've done something in the code here. You don't need to worry about it too much how I made this visualization. But I created the plane, this plane here, using the predictions. And I think now if you hover over the dots, what's cool is it tells you for each car. No, it doesn't tell you the name of the car anymore. That's kind of annoying. But so let's look at a specific car here. I don't know what car this is. Let's scroll out. Okay, so see, here's a dot here, and it shows for this specific car, which has a horsepower of 48, this weight, the actual miles per gallon is 30. I think I actually have that flopped. Sorry about that. I think the actual is 32 miles per gallon. I mean 43, and then the predicted is 32, because that's like if you took this point and projected it onto the plane, that's where they're getting the predicted value. I'm sorry, actually, I just noticed the actual and predicted are swapped. But yeah, so anytime there's a difference between, like, since these points don't lie directly on the plane, that's an error, and that would be computed in the MSE. And again, now we have two features, weight and horsepower. Those both get multiplied by some weight in our model, and so this is how a neural network can represent a multivariate linear regression. Okay, we have 3 more minutes. That's good. So the next talk, we're going to talk about a much more powerful model, and by that I mean we can capture much more intricate relationships. But it comes at a trade-off. So the model we have so far is very interpretable. Linear regression is. And what I mean by that is, see how there's this coefficient in front of weight? And how I can interpret this to my engineers is by telling them, hey, look, if you took off 1 pound, if everything else held constant, if you take off 1 pound of weight, your overall miles per gallon will go down by 0.00, or will go up by 0.0058. And they might really like that, because you can interpret why your model is making the prediction it is. And so that's very nice. And there's some other stuff here. However, what happens if we try to model more complex relationships? It becomes very hard to interpret the model. And so, like in this case, say we had some arbitrary function that's nonlinear. So in this case, like a cosine. And say, so our model was, I don't know why it'd be this, but say our model was that we found out that miles per gallon was the cosine function of 0.0058 times weight minus 10. Well, if that's the case, then how can I easily sum up and say a 1 pound increase in weight results in what for MPG, right? It's pretty complicated. Like, you can say it, but it's there's not a lot of intuition for it. So that's what I mean by interpretability. And so even maybe say theoretically that our cosine would handle it better, would be a better model, but a more accurate model, but we lose interpretability. So there's a trade-off there. So linear regression that we've covered right now is it's highly interpretable, but very low accuracy because it's very simple. Next, we're going to go to decision trees and random forest in the next lesson. So you're going to learn how to do more accurate models. Companies care, very practically, companies care about both of these. And maybe in the next one, if we have some more time, we will talk about both of them. Just one last thing, and that's the take-home challenge. So if you've liked what you learned and you want to extend on it in your own knowledge, you can try this take-home challenge. And see, you can try your hand. All the code should be in this notebook to complete these challenges. And you can submit the answer here by typing some value. So maybe 44, and I can press play, and it will say incorrect. So you have to find the right value for W&B. And then these last few challenges can be more mathematical and theoretical. And if you have your own project that you're working on, you can do this project work. So with that, I'm going to finish up. Thanks.
All right, awesome. Thanks, Josiah. We're going to open up for Q&A in a bit, but before that, we just have one quick thing to do. As you all know, this is the Datathon Bootcamp, and we're going to use the experience and the feedback from this to make the Datathon even better. So it'd be really awesome if you all could fill out this feedback survey. I've just posted the link to it in the chat. It'll just take 2 to 3 minutes of your time. And we'll take about 3 minutes of a break, so Josiah can, get water, and y'all can get time to fill out that survey. And I think we'll resume around 5:54. Cool.
All right. Hello, guys. Can you hear me?
Yeah, Samad. Yeah, we can hear you.
Awesome.
Cool.
Cool.
Yeah,
So
we can go ahead. Oh yeah,
Yeah.
we can go ahead and start with the Q&A. But just as a note, Samarth is going to be the moderator for the next, for the second half of the class. So welcome, Samarth. Give a quick introduction.
Yeah, sure. I'm another organizer here. Hope you guys had a good time today. We just got the second half of this. And yeah, hope you guys filled out your surveys as well. Let's get ready to learn and ask some questions. Okay, so where are they? All right. Oh man, I gotta scroll. Okay, so
I think I think most of our questions are answered, but if you all do have more questions, definitely post it in the Zoom chat or just unmute yourself and ask any more questions.
yeah, definitely. Yeah, drop them in the chat or just unmute your mic. It makes it a little less impersonal. Definitely want to keep this conversational.
So I got a question for performing linear regression on all the features. Yeah. So you can definitely do that. And as I think someone else responded in the chat. Oh, wait, can you hear me? Am I unmuted? Okay, yeah, I'm unmuted. Okay, cool.
Yeah, we can hear you.
Okay. So yeah, you could do it on all of them, and it would be really easy to. Well, all the numerical values. Linear regression doesn't. There are ways you can do. You can use the numeric value, or I mean the text values here. It's a little bit more complicated out of the scope of this conversation. But yeah, we can throw as many in here as you did say. And someone else responded. Yeah, I did 2 features for visualization because we can't visualize more than that. But it's really easy if you want to if you want more features, you just put it here. So like maybe, you know, I forgot what else there is. Maybe acceleration. So yeah, and then just run it. Nothing else changes. So that's how easy it is. Yeah.
Someone asks, what sort of ML skills are needed for jobs?
It depends what job you want. And Isha gave a great lecture on data science jobs before. So there's actually a difference between a data scientist and a data engineer and a machine learning engineer. And the differences are a lot to get into. I have a whole nother talk on that. But data science is, if you're a data scientist like Isha, you might just use sklearn. You probably won't ever even use any neural nets except at a very high level. But you'll use machine learning like we are here, where like we want to predict a value. So definitely know sklearn. I mean, it's nothing to brag about because it's kind of like an expected skill that you know sklearn, and you should definitely know the theory. You don't want to be one of those. That's why we went over theory today. You don't want to just blindly run sklearn algorithms. So read up on how it's working. There's stuff I couldn't cover here. And beyond that, if you want to be a machine learning engineer, this doesn't even scratch the surface. Most machine learning engineers are really actually deep learning engineers, and your entire life will be perfecting like deep learning models, as it will be much more like what Ankit was talking about in his last hour. He was talking about computer vision. And so he was talking about architectures, and deep learning is a field to itself. But yeah, so if you want to talk offline, a data science engineer or a data scientist will probably just need to kind of know like what we're covering today, sklearn type stuff. But a machine learning engineer will need to know all about deep neural networks, TensorFlow and PyTorch and all that stuff.
Yeah, and to follow up, I guess just really quickly, what kind of, I guess personally I wanted to ask, machine learning, that can be like more of what we saw today, but is deep learning more like involved, and what kind of credentials, I guess, are needed for those kind of jobs? Because I know those are like, they're looking for PhDs or master's students.
Yeah. I mean, that's nice, but a lot of big companies don't really care about that anymore because there's such a need for these. Like Ankit, I mean, he's probably smarter than most PhDs anyway, but he that gave that talk last time, but he was a deep learning engineer at Facebook last summer. And he's not even done with his undergraduate. And so you can definitely, you don't have to have a master's or PhD for that. And Isha's not a, she's just got her undergraduate as well. So you don't have to have those qualifications. You should be very comfortable in math. As soon as you get into deep learning, you will be you'll be reading a lot of math symbols and math equations, and you should be comfortable like at least getting intuition about that. And then you should be pretty good at coding too, because deep learning projects can get pretty big. And yeah, there's a lot more to it.
Yeah. And Ashley forgot to ask a question on someone's behalf. Someone says, oh, great talk. Yeah, I can confirm. Do you also elaborate ML to use nonlinear variables?
Mm-hmm. Yeah, absolutely. Nonlinear. Okay, so nonlinear variables. There's really only 3 types of variables. There's numeric, ordinal and categorical variables. So I'm not really sure what you mean by nonlinear variables. Now there's nonlinear relationships. There's also, I mean, most of life is nonlinear relationships, but I'll try to answer both of those depending on what you meant. We're gonna, in the next talk, learn about how to use, in this talk, we've only used numerical variables. In the next talk, we'll talk about how to use categorical variables, like, you know, the country of origin, the origin country here. Oh, nonlinear relation. So by the way, I'll just finish this, but origin is like it's a not numerical variable. So you need something more complicated. Nonlinear relationships, yeah, in the next talk, we'll talk about how to model very nonlinear relationships with decision trees. With linear regression, you can't really model nonlinear relationships, but it's a little bit more complicated than that. But yeah, linear regression, I would stick to very simple. I don't actually use linear regression that much in data science. It's just a good place to get started. But in the next talk, we'll talk about nonlinear relationships.
Yeah, that's a perfect segue then. I think we can just dive into part 2.
Cool.
Yeah, is everyone ready? All right then. Yeah, take it away, Josiah.
Okay. For part 2, okay, I wonder if I should give people a break, but I guess take a break if you need it.
Yeah.
Yeah.
I guess we can do that actually. Yeah. Sure. Do you want to start up in about 4 or 5 minutes?
Let's start in like
Maybe
2
10.
minutes at 6:04.
Okay, sure.
Yeah.
6:04 it is.
Stand up, stretch.
Is it 6:04? Oh, okay. Yeah, right on time.
Okay, cool.
Can you share that link on maybe the chat?
Yeah, just did.
Oh, okay, perfect.
Yeah.
Oh yeah, I just saw it.
Cool. All right. So in this talk, we're gonna this is the second part of machine learning, where in the last talk we focused pretty primarily on theory, just using linear regression as a good segue to teach some concepts. But in this lecture, we're going to be pretty practical, and we're going to talk about a machine learning algorithm that is used widely. It's still state of the art. If you don't know any other machine learning algorithm, you should know about the one we're going to talk about today, because I still use it on all my projects. It's never failed me. It's one of the best learners, super interpretable, very easy to fit. It's fast. And so yeah, for that reason and many more, a lot of people use it. So buckle in. We are going to do some cool machine learning. What I'm talking about is decision trees. So we're going to start by talking a little bit about classification, how that differs from regression. So in the last talk, we mentioned regression, which in regression, the target variable is a numerical variable. And so percentage of grade is a good example of a regression problem. So the first thing you need to ask yourself when a company gives you a data science challenge is the thing that I'm trying to predict. Is it a numerical variable like percentage, or is it a categorical variable like pass or fail? That's when it's only two categories, that's called a binary classification. So that will determine, so there's some algorithms that are only good for regression or classification. Linear regression is only good for regression, obviously, but decision trees that we're going to talk about today are actually good for both classification and regression. That's one of the many reasons I like them so much. Some other examples of classification are marketing applications, such as predicting a customer's propensity to purchase a product or halt a subscription. That's like a yes or no. Or maybe whether a customer is going to default or not default on a credit card. Actually, credit card companies love data scientists because if you can determine if someone's going to default or not, you can determine if you should give them a loan or not. So I know people that work for credit card companies. Decision trees are interpretable machine learning algorithms. So I'm going to start with a video like I did last time about decision trees. We're only going to get through a little bit of it, but it will give you an introduction. Here we go.
Here's a simple decision tree. If a person loves StatQuest theme songs, then that person is awesome. And if a person does not love StatQuest theme songs, then that person is slightly less than awesome. In general, a decision tree asks a question and then classifies the person based on the answer. It's no big deal. This decision tree is based on a yes-no question. But it is just as easy to build a tree from numeric data. If a person has a really high resting heart rate, then that person had better see a doctor. And if a person does not have a super high resting heart rate, then that person is doing okay. Here's one more simple decision tree. This decision tree is based on ranked data, where 1 is super hungry and 2 is moderately hungry. If a person is super hungry, they need to eat. And if a person is moderately hungry, they just need a snack. And if they are not hungry at all, then there's no need to eat. Note, the classification can be categories or numeric. In this case, we're using mouse weight to predict mouse size. Here's a more complicated decision tree. It combines numeric data with yes-no data. Notice that the cutoff for resting heart rate isn't always the same. In this case, it's 100 BPM on the left side and 120 BPM on the right side. And the order of questions on the left side, first about resting heart rate, then about eating donuts, doesn't have to be the same on the right side. On the right side, the question about donuts is asked first. Lastly, the final classifications can be repeated. For the most part, decision trees are pretty intuitive to work with. You start at the top and work your way down and down till you get to a point where you can't go any further, and that's how you classify a sample. Oh no, jargon alert! The very top of the tree is called the root node, or just the root. These are called internal nodes, or just nodes. Internal nodes have arrows pointing to them, and they have arrows pointing away from them. Lastly, these are called leaf nodes, or just leaves. Leaf nodes have arrows pointing to them, but there are no arrows pointing away from them. Now we are ready to talk about how to go from a raw table of data to a decision tree. In this example, we want to create a tree that uses chest pain, good blood circulation, and blocked artery status to predict whether or not a patient has heart disease. The first thing we want to know is whether chest pain, good blood circulation, or blocked arteries should be at the very top of our tree. We start by looking at how well chest pain alone predicts heart disease. Here's a little tree that only takes chest pain into account. The first patient does not have chest pain and does not have heart disease, and we keep track of that here. The second patient has chest pain and heart disease, and we keep track of that here. The third patient has chest pain but does not have heart disease. The fourth patient has chest pain and heart disease. Ultimately, we look at chest pain and heart disease for all 303 patients in this study. Now we do the exact same thing for good blood circulation. Lastly, we look at how blocked arteries separates the patients with and without heart disease. Since we don't know if this patient had blocked arteries or not, we'll skip it. However, there are alternatives that I'll discuss in a follow-up video. Remember, the goal is to decide whether chest pain, good blood circulation, or blocked arteries should be the first thing in our decision tree, aka the root node. So we looked at how well chest pain separated patients with and without heart disease. It did okay, but wasn't perfect. Most of the patients with heart disease ended up in this leaf node. And most of the patients without heart disease ended up in this leaf node. Then we looked at how well good blood circulation separated patients with and without heart disease. It wasn't perfect either. Lastly, we looked at how well blocked arteries separated patients with and without heart disease. Note, the total number of patients with heart disease is different for chest pain, good blood circulation, and blocked arteries because some patients had measurements for chest pain, but not for blocked arteries, etc. Oh no, it's another one of those ghastly jargon alerts. Because none of the leaf nodes are 100% yes heart disease or 100% no heart disease, they are all considered impure. To determine which separation is best, we need a way to measure and compare impurity. There are a bunch of ways to measure impurity, but I'm just going to focus on a very popular one called Gini. To be honest, I don't know why it's called Gini. I looked around on the internet and couldn't find anything. However, if you know, please put in the comments below.
All right. So in the rest of the video, he goes into what is Gini and the actual equations. It's a pretty simple equation to calculate Gini, but the idea is, at least for a binary, that Gini is a measure of impurity in each node. And as he talked about, we would want to find questions in the decision tree that lead to the most pure of nodes. And so Gini impurity will be, I believe, 0 if the Gini score will be 0 if the node is completely pure. And that means that we've correctly classified, by asking the right questions, everyone in that node. Versus, at least in a binary case, if there's exactly the same number of no's and yeses, then that's the most impure possible, if there's the same number of no's and yeses. And so that's the most impure. So the Gini score there is 0.5. So I highly encourage you to finish watching this video, at least for the intuition about how the machine learning finds the right questions to ask. But the intuition behind it, and from our last talk, we talked about a loss function and the computer wanting to minimize a loss function, right? So Gini is our loss function, and the computer wants to minimize the Gini. And remember, our two qualifications for the loss function is one, that's differentiable, and two, that it's always greater than 0. And so Gini is 0 or above, and so yeah, it satisfies that. And so the Gini is a loss function that the computer is going to be trying to ask different questions, look at each feature. So it goes through each feature in your data set and says, is this a good question? If I ask this question and divide my data based on the answer to this question, then will the nodes be as pure as possible? And that kind of says, okay, it's a good feature to ask, right? It's kind of like the game of 20 questions, if you've ever played that. The goal of the game is to come up with the best questions that most narrow down your possibilities. So, asking if there's chest pain is probably a good question to determine if the person has heart disease or not. But as you can see, it's not a perfect question. People with heart disease are more likely to have, with chest pain are more likely to have heart disease, but it doesn't mean that they for sure have heart disease. So yeah, I'd recommend watching the rest of that video. The link is in the Colab under Intro to Decision Trees. Okay, so next, to comment, many state-of-the-art extensions built on decision trees. We're going to talk about one of them today. And the really cool thing about decision trees is that they can be used for regression problems. And we're not going to go into too much about how they do that, but it's the same kind of thing. And so that's why one of the reasons decision trees are so nice is they can be used for both. And there's really cool, I mean, people are still building on decision trees, still squeezing stuff out of them. A really cool paper out of Berkeley just appeared a couple months back that actually combined neural networks and decision trees. Each node is a neural network, and it's pretty cool. Because decision trees are so interpretable, but neural networks are so powerful, it combines those two. So we're going to go into an example that we're going to use a decision tree to classify what kind of iris flower we're looking at. And this is, I mean, if you've done any data science, you've probably ran into, or machine learning, you've probably ran into this problem, this data set. It goes all the way back to 1936 with Fisher's paper. It's a classic in the field, but still used today. I don't know why. I'm sure there's better data sets out there, so I apologize for using something so hackneyed. But yeah, in this data set, there are 4 features, which are the septal length, the septal width, the petal length, and the petal width. And then there's a column for the target variable, which in this case is a class categorical variable. And it says if the flower is a iris setosa, versicolor, or virginica. And those are 3 different species. I don't know if that's right. I'm not biology. I'm going to call them species of the iris flower. So first, we're going to look at, I'm going to import the data set and look at some of this data. And so this is a really powerful visualization. I really like it for data sets. It's called a pair plot. It's from Seaborn. Maybe Seth covered it. But what you can see here is that it's plotted all the data. How many flowers? 150 flowers. Okay, so they took 150 samples, and it's been colored already for you by their class. So blue is setosa, red is versicolor, and green is virginica. And you can see on this pair plot, every element in this pair plot shows, except for the diagonals, I'll cover that in a second, shows a feature against another feature. And also this is a symmetric matrix, so these 2 pair plots are exactly the same, just mirrored. So I'm only going to focus down here. So here are a bunch of setosa flowers that it looks like they have very low petal length and very low petal width. And so maybe to classify setosa flowers, we could ask the question, intuitively, it seems like it would be a good question to ask, to say, we could ask the question, is petal length less than 3? And if we just ask that single question, it seems like we can classify all the setosa flowers. Because if the answer to that is, yes, it's less than 3, then we're like, okay, it's a setosa flower. And we would get a Gini score of 0 because we perfectly identified all the setosa flowers. But let's look at the other 2 classes, which are versicolor and virginica. If we just look at petal length and we try to ask the question, is petal length less than, like, say 5? It seems like that would be a good question to ask, but we couldn't say for sure that it's a specific kind of flower, because see, there are some virginicas that have a petal length of less than 5. On the diagonals, this is a distribution plot of probability distribution. Might be a little bit too much to get into at this point, so I'm going to skip that. So now I've chosen the feature names, target name. I'll go back and forth between using like X for features and Y for target. They just mean the same thing. But yeah, so I've gotten the data loaded into X and Y for our features and target. And I'm going to fit a decision tree classifier. Remember how easy it is to use a machine, anything from Sklearn. It's the same idea as what we saw with linear regression, where you create an instance of the classifier or the model, and then you just call fit with the data. And we'll get into, well, I'll just tell you what max depth is right now, or in a second. We've plotted, and then we'll plot the results. So here you can actually, and this is another really cool thing about decision trees, is it's very interpretable about why the machine learning model is going to predict what it did, and like how you can peer into the mind of the machine learning model very easily. So this is after we've done the fit. So the computer did all the magic for us behind the scenes. It's picked all the parameters. It's found all the right questions to ask. So it has to do 2 things. It has to find the right questions to ask, like features to look at, but also has to find the separation, the division point for that feature that best classifies the features. And so in this case, it's already done that. So now we get to visualize what it came up with. Now, and the cool thing about this is too, it very well aligns with our intuition, right? Because remember up above, we saw that the best question to ask just by looking at the data is petal length, petal width. Okay, so see, that's another thing we could have asked. So it's not always, yeah, so petal width. So 0.8 is right here. So we could have asked, is petal width less than 0.8? And again, that would perfectly separate the Setosa flowers for us. And so the machine learning algorithm, it always asks the best question first. And so it could have asked many different questions, but it said, you know, if I only can ask one question, what question would I ask? And that's what it's going to have at the top. And so it's asked if petal width is less than 0.8. And notice, see how there's 50, 50, 50? There's 50 samples of each, 50 observations of each type of flower. And so the Gini score here is 0.667. And so we want to minimize that. That means it's perfectly impure. So by asking no, if petal width is less than 0.8, I think left is yes, right? Left is true. So it doesn't show that, but left is true. And so all these samples are the data that after asking this question fall into this node. And so we can see that we've identified this class as the Setosa class, and all 50 samples of Setosa are here and no other samples of any other class. And so the Gini score is 0, meaning it's perfectly pure. And so we can't optimize this anymore, right? Because Gini, that's one of our qualifications for a loss function, is that it's always equal to or greater than 0. And so that tells the computer, okay, I don't need to ask any more questions. I can stop here. But over here, remember what we saw from before is that by asking any other question, we can get pretty good, but not perfect. And so let's look at this question, petal width less than 1.75. So let's look here. Petal width less than 1.75 is about right here. And so it's asking this question. It's saying samples below this go in the left node, and samples above this go in the right node as the answer to this question. So petal width less than 1.75. You can see here that there's exactly 50 and 50. So it's impure, right? And so the Gini score is 0.5. It could be lower. But by asking this question, we get a smaller Gini score, which means we're much more pure. See here, it's going to say, okay, the predominant class here is versicolor. So if a new flower came in and I didn't know anything else about the new flower, I could feed the flower through this decision tree and come up with its identification. And so based on the data that we have, if a flower came in and it had a petal width of 0.4, we'd say, oh, that's probably for sure Setosa. But what if it had a petal width of 1? Well, then we would have to ask you another question. The botanist that just came in with this new flower, they're like, I know it's an iris. I don't know what type. We ask, okay, well, what's its petal width? They say it's 1. Then we have to ask another question. Well, is the petal width less than, okay, they would say the petal width is more than 0.8. And then we'd ask, is it less than 1.75? And they would say, sure, yes. And we'd say, okay, it's probably a versicolor, but it might be a virginica. Because see, there are some samples that are virginicas. Notice how this tree only goes to 2 depth. So it could keep asking questions, right? It could keep asking questions to minimize this Gini because the Gini is not as low as it could be. However, we stopped it from doing so by setting this max depth parameter. And in Sklearn libraries, when you create the instance of the model, you can pass a lot of parameters here. And by looking at their documentation, you can see how many parameters you can pass. But max depth is probably the most important parameter to know about. And you'll see later why we wouldn't want the tree to grow further. It seems counterintuitive now, but we want to stop it there for more reason than just a visualization. So here's another example. I'm sorry, again, very hackneyed, but it's very common, popular. So you've probably seen it before, but it's the Titanic data set. And it's a common problem that we want to, given the data set that we have, predict if a person survived or not. So maybe an application of this is, say you were a data scientist at the time of the Titanic, and they're getting all these reports of people that survived and not. And maybe you have a family member that was on the Titanic, but you don't you haven't heard or not if they've survived or not. So you don't have that, but you're a data scientist. And so given all the data that you have so far and the labels of if they've survived or not, you can make a prediction of if they survived or not. And I'll even show you how you can actually even come up with a probability of if they survived or not. And so this might be, very useful at the time of the Titanic too, because they probably didn't know for a long time, is someone just lost at sea, or did they survive the Titanic? And so as a data scientist, you could come up with probabilities for survival during that time. So this is kind of everything that's going on here is more of CES stuff and getting started in data science and pandas, things I'm not going to really cover that much. But we fill NA values and stuff. Okay. This one might be kind of important. So the get dummies function does a one-hot encoding. So see here class, how a class is third, first. So one thing that random forest cannot, or decision tree cannot do, is it only understands numerical values. And so there's two ways we could convert this class feature into numerical values. One is we could just change third to 3, first to 1, second to 2, and that actually would work just fine. But another way we could do it is by creating dummies, or what's called one-hot encoding. And what that will do is, I don't have a good, yeah, I can show you. I didn't run these in order, so. Oh yeah, it's complaining. Should I go through? Should I spend time? Yeah, okay, this should be easy to run. Okay, so a dummy variable or one-hot encoding takes a class feature, like an object, right? Like this third, first, second, that the computer doesn't really know how to understand. And it creates however many levels there are to this feature. So in this case, there's 3 features, so it'll create 3 columns. And in this case, like the first sample, the first observation, that person was third class, right? And so it'll create these binary rows where the first person, now there'll be a 1 in the third class and a 0 in second and first. That's why it's called one-hot encoding, because we put a 1 in one column and a 0. I don't know. So anyways, and then you can see how this person was first class, and so you can see why there's a 1 there. So that's a good way to encode variables for machine learning problems. This is also what you would have to do in the case of linear regression, if you wanted to use linear regression with a categorical variable. Okay, don't do this if you have like way too many categories. Like if your category, if you have way too many categories, then this, this matrix will just be way too huge. Okay. So anyways, so that's what we do, and I'm not going to go into the rest of this, but you can see these features. So in the last lesson, we only talked about 2 features. In this case, we're going to talk about way more. We're going to use if they're male or not, the fare that they paid for the Titanic, if they're second class, if they're third class. Notice we didn't put if they're first class, because that's going to be that's linear, that's dependent on the second and third. So if these are both 0, then we know they're first class, so that's not adding any extra information. This feature is how many siblings or parents they had on the boat, and this is their age. So maybe we know about this about a loved one or a colleague, and we want to know if they survived or not. And then we're going to try to predict if they survived. Okay, so we're going to use a decision tree to determine this by just calling. So you see we fit max depth, and we put another parameter. I don't have time to go into this one right now. It's probably not that important. I could have taken it out, but you see we did .fit, same thing, always and then we just plot. Okay. So let's see what the decision tree came up with. Well, first, okay, so male is a binary variable. If we look at this feature of male, let's look at it. Male. Will it complain? Oh, no, it won't. Okay, so male, the first person, I did some feature engineering over here, but so see how the sex is male? So that's why there's a 1 there, meaning they are male, and then 0 would mean female. Okay, so by asking, so the computer doesn't know, like by asking if it's less than 0.5, that's asking if they aren't, if they're female, in which case true would be this direction. So a little confusing, but that's just how binary variables work. Okay, so okay, so you can see in the first node, if we didn't ask any other, I'm covering up all the other nodes and just showing the first one with my hands, but you can see that. But in the top node, you can see that if we couldn't ask any questions, we would predict that everyone died. And that's because, so say like I didn't know any information about my loved one, but I heard that most people died in the Titanic, then I would have to assume that my loved one died, or my colleague. I shouldn't use loved one, that's maybe a little morbid. Colleague maybe is a little less than personal. Okay, so yeah, because most people didn't survive the Titanic, right? So that would just be my default assumption, is that the person didn't survive. And you can see the value being 549, those are the people that didn't survive. And so that's what we would have to assume. But if we were allowed to ask a question like, well, if they're a male or not, and the person would say, no, they're female. And so then we can actually look and we're like, okay, actually, most females survived. And so we're not sure, because still some females didn't survive, but we think that they actually probably survived. Whereas if they're a male, then their chances aren't looking as good. But we could continue to ask further. So say we wanted to go the male route, we could actually ask, well, were they a young kid? If they're less than 6.58 years old, these are the babies. So this is maybe where you heard about the Titanic, that the females and babies were the most likely to survive. So you can see that here. So even if if they're a male, they most likely didn't survive. However, if they were a baby, under 6.5, then actually they probably did survive. Versus if they're older than that, then it was more likely that they didn't survive. And you can see how the Gini score is decreasing with each question. And so if we allowed the tree could keep expanding, and you could keep asking questions to determine if they survived or not. So very interpretable. I love that about decision trees. It definitely agrees, yeah. And I do see that there just popped up a question. Combine multiple attributes into one question. So yeah, that's the question. If we can combine multiple, I'm guessing like, could we ask in one node if they're a male and if their age was less than 6.5? No, we can't do that. We can't do that in one node, but that's the purpose of like 2 nodes, is that like by moving down the tree and answering those questions, we're kind of like combining those questions and the answer to those questions. So that's when we move down the tree, it's like combining answers to those questions. But you can't do that in one node, in one decision, yeah. And so a cool thing here is, say you're working for the Titanic company, and you have all these people that are coming to you that just heard that the Titanic crashed, and they want to know if their colleague survived or not. And it's a crazy time for you. You don't know. You're just hearing some reports come in, and so you ask them, okay, well, were they male? No, they're female. Okay, chances are looking a little better. Tell me, were they 3rd class? No, they're 1st class. Okay, then they most likely survived. And you're having to answer these questions all day long. And so I know the computers weren't up back then, but say they were, and you're a data scientist working for the Titanic company, and you saw that you were getting flooded with questions like this, and you couldn't answer them all, right? And so you build a little website, and you put this on the website. And in the back end of this questionnaire, there's your machine learning model, right? And so if someone's able to check this for their colleague, and set certain parameters for how much they paid, if they're a male or not. Okay, so, hey, yeah, my friend was male. He didn't pay very much. He was third class. He didn't have any siblings on board, and he was pretty old. Okay, so let's see. Chances aren't looking too good that he survived. So how about a female who paid a lot and was second or first class, maybe had some siblings? Very high chances of surviving. Okay, so if you're a data scientist, you made this for a company. Now the Titanic company is very happy with you because they're able to get to the important other stuff. Okay, so anyways, if you want to do that in Colab, by the way, that little trick, it's pretty easy in Colab. I don't have time to go into how I did that. It's not the purpose of this talk, but it is a nice little tool that you can then give to. Yeah, it's nice. Okay. So here I show that decision trees can be used for regression as well. So now I'm going to change it up a little bit and try to predict the target being fair, how much they paid, using different features, right? So fair is a numerical value. So we're going to use regression instead of classification. And so you can see that absolutely nothing changes. Well, okay, no, actually, no, something does change. We're going to use decision tree regressor instead of up here, we used decision tree classifier. That's literally the only thing that changes. They're both from Sklearn. And we can move forward and everything else is the same. So here we're trying to predict fair. And so what if, in the same way, the top node represents, if we didn't ask any questions, how much did people pay? And you see it's predicting $32. And if we looked at the data set, df.fair, we get like how much people paid. Now if we do df.fair.mean, we can see that people paid on average $32. So that's pretty intuitive, right? The decision tree is saying, if we don't get to ask any questions, I'm just going to say, your fare is going to be $32. However, then if you get to ask a question like, well, are you going to pay are you going to be third class or second or first? And so say I responded, yes, I want to be third. Wait, this is a little confusing. Third class being less, so that'll be false. So that'd be going this way. So you can see, or third class being true, going this way. So here you can see what third class people on average paid, right? So the top node is what everyone paid. And then by asking certain questions, you can get down to more specifics of what a fare would be. And so, this is second or first class people paid on average $54, and then so on and so on. So yeah, that's regression because the value that you're predicting is a numerical value. And so decision trees can be used for both, which is awesome. Decision trees for the win. Okay, well, in a quick 15 minutes, we're going to try to cover, 10 minutes. Oh, we're going to try to cover a very important part of machine learning. Hopefully, you can use decision trees and what we're going to learn next in the Datathon and in a data science project, but you need to know how to avoid overfitting and what that is. So we're going to talk about test train split, and why, and I'm going to talk about why did I set the max depth on these instead of allowing the tree to go as deep as possible. Okay, so overfitting is when we do the dot fit, but our model is able to capture the data so well that it's almost like too good, right? So this is kind of similar to in class. We want to learn the material and be able to generalize it. And so that's the whole purpose of, in class, we get training material, like the slides and even the homework they give us is like training material. But the idea of a test is they want to give you problems that are kind of similar, but that you've never seen before. And how well you do on homework kind of doesn't matter, especially like in grad classes, right? Like homework, they're like, oh, this is just for you to get better at it. But what really matters is the test. And that's because a test shows how well you can generalize your knowledge. And being able to generalize knowledge is really the true measure of intelligence, right? Being able to just memorize questions and their answer isn't as much a measure of intelligence, even if it's how a lot of us get through school. But so what this graph shows is an example of overfitting. So here we have some data, and on the left, we'll see that the dashed line is the model, right? And so on the left, the dashed line, we can see it tries to fit the data, but it's obviously just too simple of a model. So it's what we call underfitted. Yeah. Whereas in the middle, we call that like a good fit, because the model seems to capture the trend of the data. Whereas an overfitted model will try to capture every data point and be so specific to that data point that if we get a new data point, it won't be able to predict that new data point too well, because it's just so well learned the data that you gave it. And so that's kind of like in class, if you just memorized every problem you saw in class, you'd be able to do very well at those problems you saw in class. But when you got to a test question, you might not know how to solve it because you just learned so well the problems in class. And so that's kind of why I didn't allow my decision tree to grow deeper, because if I allowed it to ask so many questions, then those questions would become specific to like a single person and if they survived or not. And it might not generalize to like new people, right? And so by forcing it to only ask a few questions, we can force it to be a little bit more general, even at the cost of like a little bit less accuracy on the training data. But yeah, if we let it like ask every question, it'll be able to perfectly identify each person, but not be able to generalize. Yeah, okay, that's enough for that. So there's two reasons why overfitting happens. It can either happen because our models are too complex by design. So a decision tree, right, it could get very, if a decision tree gets very deep, then that's a complex model. It's asking all these questions, it's overfit the data. Another way it can overfit is if we train too long on our problems, and that I can't get into. So, but the number two is like, well, what if we just study the same questions, like the class questions, over and over again? We're eventually just going to get like to know them by muscle memory, right? And we won't really be able to generalize our knowledge. So how do we mediate that? Is by doing a test train split. And so the same thing for class, right? They give you some problems in class, and then they hold out some problems for your test. And the test is really how well you learn the material. And so through Sklearn, we can do that very easily by doing a test train split. And so we'll test train split our data. And stratifying allows us to make sure that we have the same number of class instances in both our test and train. And so you can see that the percent that survived in all the data is the same as in the test and train data. This is wrong. This should be train data. Okay. Nope. This should be train data. This should be test data. Okay. So how well does our decision tree classifier do on training score? Okay, so check this out. So an overfitting graph kind of looks like this. As we allow our decision tree to grow deeper and deeper, the predictive error, which is inverse to our accuracy, goes down and down. So this is like a loss function, right? So we can get better and better at predicting if people survived or not on the Titanic. But eventually, if we allow our decision tree to grow so deep, then our test, it becomes overfit on the training data. And so the error goes super low on the training data. We perfectly classify all our training examples, but at the cost of not generalizing well to our test data. And so what we're going to do is play around with this a little bit.
I just wanted to hop in really quickly. We've got about 5 minutes until we can start doing some Q&As.
Okay, thanks. I didn't run them in order.
Brian is asking, it says target is not defined for the test train split.
Yeah, I see that. Target. Try Y here. Okay, sorry about that. do Y, fill it in with Y. Okay, so right, so if we let our max depth be 2, note the training and testing score and remember that. Now, what if we allow our max depth to get deeper, like, I don't know, 8. Now, what's happening is we're moving to the right on this graph. And so we're allowing our complexity of the model to get further. So we might expect our training and test accuracy to go up as our error goes down. And that's exactly what we see, right? So training score has gone up and testing score has gone up. But what if we allow max depth to go super deep, 100? Then what was testing score before? Okay, well, this might not be a perfect example. Okay, well, this isn't a perfect example because it seems like it's not overfitting. But see how the training score has gone up, but the testing score hasn't gone up at all. When I was testing this earlier, actually the testing score went down, which would agree with this graph. So maybe this example is not working. But the idea is, if we allow our model to get so complex, then our training score will go down. Okay, only have 4 more minutes. Cross-validation, I'm gonna have to go over this really quick, sorry about that, is just doing test train split over all multiple times over your data. And so when you do like Datathon or a data science project, you should in the end do a cross-validation to accurately represent how well your model's doing and get the score. It's just doing test train split a bunch of times over all your data. And so it's gonna be the most robust way to report your score. So random forest are another way so most people actually don't use decision trees in like production projects. They'll use random forest, but I wanted to cover decision trees so in depth because a random forest is just a collection of decision trees. And random forest is, in statistical terms, something we call bagging, which I forgot what that stands for, but just imagine a bag of decision trees. And how it works is you just get a lot of decision trees, and you fit them on different subsets of your data, okay? And then you do like a majority voting. So you ask each decision tree, did this person survive or not? And then you just do, well, what did most of the decision trees say? So it's kind of similar to if you're trying to pick a movie by asking friends. And also, so each decision tree in the random forest only gets a subset of your observations and also only gets a subset of the features of the data set. So it's kind of like asking a group of friends, like, what movie you should go to. Each friend has a subset of your interest in mind. Maybe one person cares about the actors, another person cares about the cinematography, another person the music. So each friend kind of cares about something different. And they've also all only seen like maybe a subset of the movies you've seen. And so they're all going to be able to give you like a little bit different decision of movie you should go see. And you can just do a majority voting to decide what movie you should go see. So you're going to want to probably do a random, you can do in like your data science project, a decision tree and a random forest. The decision tree is really nice because you can visualize it. Theoretically, you could visualize a random forest too by like visualizing every tree, but it just doesn't work as well. But the random forest, because, you know, in the same way that like, if you ask a lot of different friends and majority vote, you'll be more likely to like the movie kind of, instead of just like asking one person, that person could be wrong. And so in the same way, a random forest is going to be able to generalize better because each random forest only like gets a subset of the features and of the data. It'll be able to generalize better. So here we just and notice random forest exactly the same as the decision tree. It's just we call it random. I mean, as far as how we call it, we can also set the max depth on the random forest, and we can get the testing score. And you can see that the testing score is a little bit higher, not a lot, but a little bit higher than the decision tree in this case. In a lot of cases, the decision tree won't learn at all, but the random forest will. So this is kind of a toy example. And again, the cross-validation here shows this is really the score that you want to show off at the end of your data science project. I think this is the last thing, because I know it's 50, is feature importance. And so another really cool thing about decision trees and random forests, because random forests are built on decision trees, is that it's really easy to get feature importance from a model. So remember, our model was called classifier in this case, and literally just feature importance, and we just visualize that here. And remember all the way back up to the decision tree, the most important question to ask is if they're a male or not. And so that's one way to see feature importance. And then you can see that if they're third class and their age is also an important feature. And that will agree with this plot down here. That you can see that if they're a male or not was the most important feature, but the fare that they paid and the age was also a very important feature. And so that's, I mean, I love reporting feature importance. Companies really care about this. Like, say you're trying to classify if someone will buy a product or not, and you have a bunch of features, like maybe how much money they put into the ad campaign, like where they marketed it and everything. To be able to tell the companies like what features are most important to if the person bought the product, I mean, that's just as important to the company as being able to have a high accuracy. So you want to say, hey, look, the amount of money you put into the campaign really does matter for the if they bought the product or not. Not going to be able to get into hyperparameter tuning. Just remember like max depth. That's called the max depth. Remember how we fed that? That is a hyperparameter, and you might have to try a bunch of different hyperparameters, a bunch of different max steps to figure out what's best for you. Or you can use this thing called grid search, which just tries a bunch of combinations and will pick the best hyperparameters for you. That's a way to like improve your model performance. And decision boundaries, we definitely don't have time for that, but look through it if you want. Beyond accuracy, we do not have time for that, but look through it if you want. And I just want to leave you with random forests are awesome. And for 95% of the things you do, a random forest will be great. But multiple additions have been made to the random forest that really are state of the art. So if you want to learn more past random, so we learned about decision tree. The advancement to decision tree is random forest. The next advancement to random forest is added boost. Added boost, and there's an advancement to that called gradient boost, and then XG. So there's more advancements, but they're all built on the decision tree. It's just how we build it. It's how we combine the decision trees and everything. But I've included some videos here about going from one to the other and comparing different methods. If you have time, but if nothing else, just use a random forest. You just might be able to get a little bit better accuracy. So here's how you can import an added boost and an XG boost, and you can use them the same as everything else we've been doing. So I've also included a project here. Sorry, Samart, I'm killing you as the moderator here. I'm not giving you a chance.
Okay.
No, I'm almost done. But the project work is, I found this really relevant data set. I've not done this project. I just created it yesterday. If you're wanting like a project, I think this is something you could show off to. I do apologize. It's probably a little bit morbid, but it's very relevant. So there's probably actually people, it has to do with COVID and the death rate, and trying to, there's this new country that doesn't have adequate testing. It's your job as a data scientist. Maybe you're asked by the CDC to predict how many new deaths they had. And even though they don't have good testing. So you're going to use this data set it's literally updated every hour. So this is a very relevant data set. And you're going to try to, this is the details of the country. And, you're going to try to determine the new deaths. So this should be a blank. Yeah, using what you've learned today. There we go. Further learning, Data Camp, Kaggle, towards data science, feel free to reach out to me. Thanks.
Awesome presentation, Zach. Thank you for putting that together. So we have a quick form, just as always. It would be awesome if you guys filled that out for us. TAMU Datathon, we're out here. We're trying to bring you guys awesome events, and it really helps if you guys give us some feedback. So check out that form. Maybe we can take about 60 seconds or so to fill that out. In the meantime, drop your questions in the Q&A. Someone asks, actually, Giselle, I'll give you a minute to get some water.
Sure.
And then also, if you guys are interested, Josiah had some links for Kaggle, and I just dropped one in that I was looking through earlier today for Seaborn. So, there's always micro lessons everywhere on really most topics, and Kaggle is a pretty good place to do it. What you saw with Colab is also, I think, on Kaggle on just a bunch of online notebooks that you can just mess around with, use their GPUs if you really want to tax the computer. Do that. Yeah. Okay. I think we can jump into the questions. Hopefully you guys filled out the form. Someone says, does max depth have anything similar to set speed in terms of machine learning?
Set speed?
Set dot speed. Is that in your code?
I don't. Could whoever asked that maybe elaborate? I'm not familiar with set speed.
Oh, seed. Okay.
Oh, seed?
That.
Oh, the seed is a random seed. So there's a lot of randomness to especially a random forest. Random forest. So in research and when you're developing these algorithms and say you're testing different, the random seed just seeds the randomness of the random forest. And that's important because without that, every time you run the random forest classifier, you might get slightly different results. And that makes it really hard to say try out different hyperparameters max depth and stuff. So by setting the seed, you can try out, you'll get replicatable results. Also, if you report the results on a research paper or something, and you want to make sure other people can get the same results, you should tell them your random seed. But theoretically, it shouldn't affect performance at all. If it is, there's something kind of wrong. But yeah, it just set it once, and literally the random seed can be anything. So that's another thing. Set it to 0, 42, whatever, as long as it just matters that it's a value. That you don't change.
Nikhil asked, he said, thanks for a great lecture. Would you be willing to talk about what you did in your internships if they were machine learning related?
Okay, let's see.
That'll probably be our last question for tonight.
Okay, so Microsoft was my first, and it was not. But in my first internship, and this is something I'd recommend, I knew I was kind of this is 3 or 4 years ago. I knew I was interested in data science, or at least I was hey, it could be cool. So before I left, I looked on the Microsoft directory, and I was oh, there's some data scientists in my building, and I just reached out to them. I'm hey, could I come talk to you about your job and stuff? And I wasn't quite interested enough at that time to ask for a job from that person, but hey, that could have been a great way to get a job as a data scientist. So I'll just say that. For the CIA, I was doing a lot of data science. Just stuff I'm showing you right now. And I was using Colab and everything, or at least Jupyter Notebooks. So, very much the kind of stuff I'm showing you. And then for Facebook, I would say it was a different kind of data science, but I was trying to I was trying to do anomaly detection. And so I was working for a part of Facebook that has a lot of, that helps phone carriers. And sometimes they're and so Facebook would provide this data to say Verizon. And sometimes it would say, hey, Verizon, half your users just left your service. And Verizon would freak out. But that was just a bug with the Facebook software and data collection. And so my job was to create a cluster or an anomaly detection that was kind of time series. And so it'd see, okay, normally this is what the data is supposed to look like. Hey, we have this huge spike, and then it would notify the engineers first, and then they'd be able to see if it was a real spike or it's just a problem with the code. So that was all in Python. There wasn't a lot of Jupyter Notebooks, although I did use it a little bit to test theories, but I was more a software engineer there. So it was really important that I was able to deploy what I came up with. And then Texas Transportation Institute is in College Station, and they're looking for data scientists, by the way. And they're an awesome, they're called Texas, but they serve the whole world, and they're an Institute of Transportation. And so reach out to me or someone at TAMU Datathon if you are looking for a job there. It could be a great way for you to get started in data science. But there I was doing more data engineering. Like I was working on cloud computing and stuff and setting up cloud infra. So again, just a very different side of data science, not a lot of this stuff. And then finally, right now I'm at Carnegie Mellon and as a researcher, and that's much more machine learning engineering or machine learning scientist instead of a data scientist. I don't do a lot of this stuff, but I more like work on the architecture of machine learning algorithms. And so it's a little bit different than this. Yeah.
Yeah, great. Okay, so as always, if you have any more questions, guys, just leave them in the Slack. I can post a link for that actually. And also thanks guys so much for joining us. I think we can wrap it up here tonight. It's already 9 p.m. Central. I don't know where you guys are, but I know good part about this is we can join from anywhere, all over the world. But yeah, thanks again, Josiah. I think we can call it here. Please, again, fill out that survey. It really helps us out. But yeah.
Thanks so much for sticking it through, guys. I wish I could see your faces. Yeah, appreciate you guys. Yeah, and hope to see you at Datathon. All right.
Yeah, see you at Datathon.
Yeah.
In October.
Yeah, that's right.
Everyone.